Hello, operating systems people. This is Gabe Palmer, and we're going to be talking today about a couple of practical examples of how you think about really scheduling on systems. And we're going to use two very different types of systems. One, Linux, which is trying to do the best thing for all applications, failing at some, but trying really hard and generally doing quite well. And then two, real-time systems, whereby we're actually building task models for systems to be able to make guarantees about their execution. So today, case study number one, a general scheduling policy in Linux that works well for most workloads. It's called Completely Fair Scheduling in Linux, which is not an accurate name, but is a good salesmanship name. And case study number two, real-time systems, real-time scheduling. And where you actually need to be able to guarantee that you have a bounded responsiveness for some bound with threads with a very specific execution pattern. So these are two systems, one that tries to do decently well for most workloads, and one that tries to do exactly well by being able to prove that it will be able to have some properties for very specific and restricted workloads. So let's dive into Linux. Linux tries to balance many different competing goals. Last class we went over some of the general scheduling goals, and many of them are important here, and I'm kind of summarizing them in these three different categories. We have IO-bound responsiveness, IO-bound tasks that wake up from some sort of an interrupt, need to do their computation often within some sort of a relatively small amount of time. They need good responsiveness. Efficient execution, we want to make use of our CPUs as well as possible, so we want them to be fast, essentially, right? That basically means minimizing overheads within the system. That's about it. And fairness, we want different threads within the system to have some notion of fairness, and we'll define what that means a little bit more. An interesting aspect of this is that most of these goals, as I pointed out last time, are inherently at tension with each other. If you want good responsiveness, it's hard to be fair, because fairness means not prioritizing IO-bound tasks. Efficient execution means that you really want FIFO, and that is not necessarily fair if you have one task that's going to go into an infinite loop. If you want efficient execution, it's also hard to have IO-bound responsiveness because you're going to be context switching more when you're responsive. So we have all of these different competing concerns, and we need to figure out some way to navigate them and come up with a policy that works well for most applications. So Linux has what's called the Completely Fair Scheduler. It was sold as that, with that as its name when it was initially implemented and kind of put before the Linux community by Ingo Molnar. And it's essentially based on previous theoretical work that was done on the earliest eligible virtual deadline scheduling. It's sad because I don't think that it actually knew about that work, but that work did come years before, and it's essentially the theoretical foundation for it. This is in the lineage of what's called weighted fair scheduling, which is a category of algorithms that were essentially mostly used for packet scheduling, deciding which packets should be sent at which points in time. So you can look that up, you can Google for that if you want to know more information about this. And the general idea behind a lot of these is that threads should get CPU time proportional to their weight, where we could define the weight for different threads to give them some notion of priority. And the general idea here is that two threads at the same weight should basically get the same proportion of the CPU, the same share of the CPU. Okay, so how does CFS work? Let's assume that we have n runnable threads, and each of these threads, which I'll call tau I, has a weight wi. So every thread, tau I, has some weight associated with it, and if we don't specify it in some way, then they all essentially can be assumed to have the same weight, right? And what we want for them to have is a CPU share that is essentially their weight over the sum of all of the weights of the tasks that are executing at the given point, that are runnable at the given point. And that's what that equation shows. You take the summation of the weights of all of the tasks at a certain point and have that be the denominator over the numerator being your weight, and that's essentially the share of the CPU that you should get. So putting this into perspective, if we have two tasks, each with the same weight, that means that you should get 1/2 of the CPU, right? Which I think is a good intuitive notion. Let's dive into the example below. You can see that we have 3 tasks, the blue, purple, and teal, and they have weights 1, 2, and 3, right? So the size of those boxes is commensurate with the weight, just to give it a little bit of a visual representation. And if we want to calculate the CPU share of the tau blue, the blue thread, then we essentially have the fraction of the system that is the blue, which is 1 weight, over the sum total of all of the other weights. So if we line them all up, you can essentially see that that essentially means that we have 1 out of 1 plus 2 plus 3, which is 6. So we should get 1/6 of the CPU. So you can see that this weight is a little bit of a way to parameterize a notion of fairness. It's not saying everybody should get the same share. It's saying, well, some of these things might be important for them to get a little bit more of the share of the CPU. So you can modify the relative weights to reflect that. CFS aims for a 20 millisecond responsiveness. And I'd like you to think about why that is. Put another way, what this is saying is that if a task starts executing, it really wants to be able to finish its execution, if it's a short-running task, if it's an IO-bound task, within 20 milliseconds, right? So it's aiming for this 20 millisecond responsiveness, and I'm going to ask why. Do you have any idea why 20 milliseconds might be important here? Pause, think about it, come back. 20 milliseconds, as we'll see later, just as kind of a little bit of a threshold that matters for a lot of different applications. Humans' perception of responsiveness can go all the way down to sub 10 milliseconds. So 20 milliseconds seems to be a nice boundary that a system might try to optimize for. In the end, it's a heuristic value, and it's actually something that you can program, so you can actually change it in Linux systems. But by default, 20 milliseconds is what it shoots for. But it also says that preemption, so the ability that we might want to take a thread, stop it executing, and switch to the next thread, we know that that has overhead, that has context switch overhead, and whatnot. We want to make sure that those are at a minimum of 4 milliseconds apart. So we never want to preempt a thread if it hasn't executed for at least 4 milliseconds. Why does Linux have this policy? This seems really strange. Pause, come back. So the general idea here is that we know that dispatch latency, context switch latency, all of these things are not free, and the Linux designers have effectively said that whatever overhead that all has, it's okay if we have that overhead every 4 milliseconds. We will still maintain a high enough utilization or throughput of the system if we have preemptions at that frequency. So this is actually an optimization to maintain a utilization of the system, a throughput of the system, right? Minimize the overheads within the system not minimize, I shouldn't say minimize, constrain the overheads of the system to happen only every 4 milliseconds. So what CFS ends up doing, if we have 2 threads, as we see in the bottom, the blue and the purple. The blue has half the weight of the purple. What Linux will do is it will actually shoot for, over the next 20 millisecond period, to be able to fit all of the execution for those different proportions of the task into that 20 milliseconds. So what we see here is it says, well, there are kind of 3 units of execution here effectively, right? So we have the purple that essentially should get 2 units of execution for every 1 of the blue. So what we're going to do is effectively say, how can I fit those 3 units of execution into 20 milliseconds? Well, we chop that 30 milliseconds up into 3 different chunks and basically make that our quantum, the preemption, the preemption latency. So what we're doing is we're always saying we want preemptions to be a minimum of 4 milliseconds apart. But if we have a few enough number of tasks and we have weights formulated in such a way that we can have a larger preemption latency, or a larger inter-preemption latency, a larger quantum, then do so. So what it's saying here is, let's actually make the quantum 6.67 milliseconds instead of that minimum of 4, because we just don't have enough work to motivate having those switches back and forth every 4 milliseconds. So if we look at the quantum calculation now, it's actually a minimum of 4 milliseconds, so we're taking the maximum 4 milliseconds and the numbers of these weights over the 20 milliseconds. And that's how we get the 6.67 milliseconds. So what Linux will try to do is effectively switch back and forth between the tasks in this specific formulation. It might run the blue task first, it might run the purple task first, but whichever one it runs first, if it's the blue one, after 6.67 milliseconds, it'll preempt it and then run the purple one. And then we're outside of that 20 millisecond boundary, it'll again just keep trying to maintain this level of interaction where we switch back and forth between them in this type of proportion every 6.67 milliseconds. Let's go through another example. So now we have 3 tasks, a blue task, the purple, and the teal, and we now want to be able to fit them all into the system. Now notice that there are essentially 6 units of execution here. So if we do that same calculation to try to figure out how big the quantum should be between them, we end up with 6 out of 20. And that is too large, or that would generate a quantum less than 4 milliseconds, and because Linux says we really want to maintain utilization of the system, we want to minimize the preemption overheads, so let's make sure that it's always 4 milliseconds or more apart. Here it will choose 4 milliseconds as the quantum. So it'll choose these 3 tasks and will execute them in proportion to their weight as such. It'll basically run the blue task first, then the purple, then the green, and notice it's kind of choosing their execution in proportion to the weight that we apportioned. But because we're executing them for 4 milliseconds each, we don't get to go through a full execution in accordance with the weight until 4 milliseconds after the 20 millisecond boundary. So it really aims for fitting all of the threads, their weight apportioned execution within 20 milliseconds, but it will not do so if doing so would have required a quantum less than 4 milliseconds. So we see that here. Let's kind of dive into the details of how it actually chooses which task to run at any point in time. What we've covered so far is effectively an intuition as to how they're trying to fit everything into 20 milliseconds for an execution of all the threads, and what happens when they can't do that because there are too many tasks with too many weights to be able to fit within that. I am simplifying here, by the way. I think that the actual policy is slightly more complicated than this, but I am simplifying. You can think of this as a proxy for CFS. There are some details that are maybe simplified. Okay, so how do we actually decide which task to execute at any point in time? The fundamental thing that we're going to be doing is we're going to be tracking how long the different threads have executed as they kind of go through their execution, right? So when we enter into the run queue, our execution time is considered to be 0, and as we are given execution, the Linux kernel will just track how long each of these threads has been executing, right? And what it will maintain is a weighted execution time of all of the threads. And that is effectively saying that we're going to track its execution time, but then divide it by its weight. And what that means is, and we're going to kind of treat this weighted execution time almost as a priority, right? If a thread is executed for much longer than another, then we probably want to run the other one before this one again, right? But the weights make that a little bit more complicated. So we're essentially just weighting that execution time, giving ones that should have a larger proportion of execution essentially a higher priority. So again, we have the weights of the blue, purple, and green, same example as the previous one. And at the first time in the system, we execute the blue task. After we're done executing the blue task, we're at 4 milliseconds into the system execution, and we're tracking that tau 0, thread 0, has executed for 4 milliseconds. Its weight is 1, so it has really executed. Its weighted execution is 4 milliseconds that it's executed divided by 1 for its weight, which of course is 4. So at that point, what we do is we look at all of the tasks that are in the run queue, and we want to choose the task to execute that actually has the lowest weighted execution. So tau 0 has already executed. So it has a weighted execution time of 4, which is higher than the other tasks, so we need to choose one of the other tasks. We choose tau 1 to execute now. So for the next quantum, between time 4 and 8 milliseconds, we actually execute tau 1, which means that it executes for 4 execution units, but its weight is 2. So we track a weighted execution time of 4 divided by 2, or 2. Right? So we've essentially said, okay, our weighted execution time of tau 0, 1, and 2 is 4, 2, and 0. We choose the lowest one to execute next, which happens to be tau 2, because of course it's 0. We execute tau 2 for a quantum, 4 milliseconds, and now we calculate its weighted execution time. You can see now we have a weighted execution time for each of the tasks in the system. So we have 4, 2, and then 4 divided by 3, which is still the lowest weighted execution time. Because it is the lowest weighted execution time right now, we will actually continue executing the teal task, tau 2. But now that we've executed 4 more milliseconds of its execution, its weighted execution time becomes 8 over 3, which now is higher than 4 over 2, right? So at this point, we switch back to the purple task, tau 1, and execute it. So now we've looked at the execution of all of the tasks, and we end up having 4, 8 over 2, and 8 over 3. So at this point, we're going to execute the teal task, which executes for 12 over 3, which executes for another 4 milliseconds. The weighted execution time tracked is 12 over 3, etc., etc. So we continue doing this. Now we can see that the weighted execution time of all of the tasks, because we've executed them all within that window we were shooting for, is 4. Right? So they all have an equal weighted execution time. So what that effectively means is that we have executed them all exactly in proportion to their weights, which is to say, if we define fairness within the system as executing in proportion to your weight, then we have provided a fair execution of all of these tasks over a window of time that tries to be 20 milliseconds so that we get good responsiveness, but might go over if for some reason we can't achieve that quantum as it does here. So this is the whole idea behind Linux scheduling. Effectively, choose a window that we're shooting for getting responsiveness in, 20 milliseconds. Choose a minimum quantum time, 4 milliseconds, to kind of bound the overhead of all of the context switches within the system. And then use this type of a formulation where we're essentially choosing the minimum weighted execution time of everything over time to execute. And the way that this is implemented is relatively simple. In addition to the bookkeeping that we were doing here, we essentially use a red-black tree, which, as I hope you all know, if you don't, then you should absolutely look into this data structure because it's very important and everywhere, is just a balanced binary tree. And it's effectively sorted by the weighted execution time. If we look at the farthest left node, then that has the smallest weighted execution time of everything in the system. So we're essentially just kind of, as we do these calculations for execution time and calculating the next weighted execution time, we just are kind of moving a node within the red-black tree to where it should now be, and then choosing the leftmost node and executing that. So the run queue data structure in CFS is just this weighted binary tree. Or this red-black tree. Okay, so just a summary. We're attempting to have a small response time. So we choose a window of 20 milliseconds in which we try to kind of run all of the tasks. It does implicitly favor I/O-bound threads, because when a thread wakes up from a block state, it goes into the run queue with a weighted execution time of 0, which means that it is, in a sense, optimizing for response time. I/O-bound tasks will get some amount of priority over CPU-bound tasks that are going to have a very large weighted execution time, right? It also tries to maintain a high utilization of the system, or put another way, try to minimize the overhead, or try to control the overheads within the system. So it essentially says that you can only have a context switch due to just quantums, due to preemptions every 4 milliseconds. Now keep in mind that a thread might make a blocking system call, or make a blocking system call and require it to block before it executes for 4 milliseconds. So this is really a preemption latency more so than kind of a context switch limiting factor. It tries to maintain fairness. If every thread has the same weight, then every thread will get run with the same proportion of the CPU, right? And that matches very well an intuitive notion of fairness. But it also enables some form of prioritization, where the threads actually receive a amount of the CPU proportional to their weight versus everybody else's weight, right? So I think that, again, matches a very intuitive notion of kind of a priority. It also has a theoretical backing, because the earliest eligible virtual deadline scheduling algorithms have kind of rigorous proofs behind it, stating exactly how much execution time you're going to get in different scenarios, right? So that's a huge benefit, whether the Linux maintainers know about that result or not. It's a big benefit that it maps well to that theoretical result that happened before CFS. But there, I want to kind of back out a little bit, right? Let's look at the forest from the trees. This essentially is an algorithm that tries to ensure that the execution properties are somewhat predictable. We know how the fraction of the CPU that we're going to get, but the formulation of that fraction of the CPU is completely dependent on the dynamic state of the system. What that means is how many threads are in the run queue at a certain point, and which threads are in the run queue at a certain point determine essentially how much CPU share we're going to get at any point in time. So because this is dependent on the dynamic properties of the system itself, we aren't making any global guarantees effectively on utilization, right? So what we are not doing for specifically is we are not saying that we are guaranteed to execute E time units within a specified window of W, right? A specified window of W, who knows what the state of the run queue is with any one of those W's, so who knows if we're actually guaranteed to execute E time units within it. So this is very, very, this algorithm, CFS, is very strong on systems where you don't know much about the system, but where you need strong guarantees about being able to execute E time units within certain windows of size W. It is not actually going to cut it. And you actually need these guarantees in classes of systems. So the second portion of this lecture, I want to talk about real-time systems and real-time scheduling for these systems, which are these systems that require strong global guarantees about execution. Okay, so real-time systems effectively conduct computation that controls the physical world in one way or the other. So you can think about this being the CPUs and the operating systems that are controlling things like quadcopters, autonomous vehicles, and rovers, right? They need to interact with the real world, which means that computation has to happen by the time that your wheel goes around one time, by the time that you go around a corner, and by the time that you need to actually engage the brakes, right? These are systems that interact with the real world, therefore the computation has to happen on the time latencies defined by the real world. Planes, trains, and automobiles are very traditional embedded systems, and also the name of a horrible movie. industrial plants, cities, power generation. These are all systems that have real-time scheduling implications, and the Internet of Things is a very popular modern instantiation of real-time systems. If you've heard of the name embedded systems are just computation usually embedded into some sort of a real-world physical system, and real-time systems typically drive the timing of embedded systems. So the question to you that I'd like you to brainstorm a little bit is how much an OS actually needs to enable these domains. And to put this question into perspective, you want to think, how is this just not computation as normal, right? How does needing to be embedded into the physical world and control the physical world, control the motors that are controlling your physical system, how is that not just computation as normal? Pause for a little bit, brainstorm a little bit, then come back. So effectively, this is really saying not just that we need to control the physical world, not just that you need to do computation, but that our computation needs to make decisions on the scale that will not just impact the real world, but make the impact on the real world by the time that it needs to happen, by the time that the world needs to be changed. And I'll go over an example of this. An example of this is anti-lock brakes. It's kind of a traditional, easy to understand example, so that's why I'm going over. The general idea behind it is that real-time essentially means that our system, our scheduler, and our computations need to have some notion of a time awareness about them, right? So if we're controlling the physical world, it means that we need to adhere to the world's timing constraints. And for anti-lock brakes, this means that we have a sensor in every wheel that effectively is sensing the rotational speed of that wheel and sensing it at some sort of a periodicity. It might be 10 times a second, it might be 100 times a second, but it is periodically sensing this rotational speed of the wheel. As you well know, we have a speedometer in vehicles, so we already have sensors that are measuring the vehicular speed, and both of these values are fed into an ECU, an electronic control unit, which is a fancy word for a computer, an embedded system. And it takes all these sensor readings in and needs to determine whether the rotational speed is starting to go significantly less than would be indicated by the vehicular speed. If the rotational speed of the wheel falls below the vehicular speed, that means that the brake for that wheel is starting to lock up the wheel, is starting to make it so that the wheel effectively will be skidding. And when you're skidding on the ground, you actually have a lower coefficient of friction with the ground, so you are stopping less effectively. So what an anti-lock brake system is trying to do is effectively have that ECU detect when we are about to skid and tell a command to the actuator, which is the hydraulic controller, effectively that it needs to let off the brakes. There's this kind of unintuitive notion that we're essentially trying to let off the brake to get a better braking behavior from the car, right? So the ECU has to make that decision and send it to the actuator in time to avoid the brake actually engaging fully and the wheel starting to skid. So all of that happens between the time when we're about to start skidding to when we need to when the actuator needs to actually undepress the brake to prevent the skid within a 300 millisecond latency. So when I say that these real-time systems have to adhere to the world's timing constraints, this is what I mean. We have a 300 millisecond latency that essentially is imposed by the physics of the real world, right? And we tend to think of this as a computational abstraction called a deadline. Now note, the electronic control unit might have a shorter deadline than that for its computation, because the 300 milliseconds includes all the way from the sensor taking the sensor reading, sending it over some sort of a network to the ECU sending over a network to the actuator, and the actuator doing its physical process to be able to remove braking pressure, right? So the deadline for the ECU might be even smaller than this. So we tend to think of deadlines in real-time systems as a computational abstraction for this real-time requirement of the overall system. Let me give you a few more examples of deadlines that we think about when we think about real-time systems. Augmented reality is quite a popular domain right now. Virtual reality is very close to this as well and has some of these same problems. Human control. So this is kind of the latency for us to be able to sense something and react to that. So for instance, going from our optical stem to our brain, making a decision, and then sending a command out to our hand. The latency for all of that is round about 300 milliseconds. And what's really interesting is, if you're into video games and your parents tell you that, video games don't get you anything, you can tell them that esports pros are some of the only people on Earth. I'm sure fighter pilots and, F1 pilots are probably included in this as well. But they've actually often trained their response time down to about 150, 180 milliseconds. So this is actually something that you can train, which is really cool. There are, of course, kind of physical constraints that you can't overcome, just kind of, transmission of electricity through your nervous system. But you can actually train to make it faster, which is really, really cool. So we actually have a latency imposed by human control, which means that if we have a human that is responding to something and they do some sort of a response, we can expect that they will do it within that type of a time window. However, human perception is much faster than that. So if we tell our finger to drag down our mobile phone, we will be able to tell that there is a lag in the computational system if the computational system doesn't move the web page or whatever it is with us on a scale of around 10 milliseconds, right? So human perception has a much tighter deadline. And that's one of the many reasons why you end up having these types of issues with augmented and virtual reality, where if you turn your head, which is kind of sensing that you are moving your body, and the computational world doesn't move fast enough being on the order of 10 to 50 milliseconds, then you can actually notice that and your brain starts to become sick. Robotics and autonomous vehicles have a lot of interesting deadlines as well. If you have a robotic hand that is trying to grasp or trying to touch something and apply some sort of a uniform force, for instance, hold something between two fingers, you typically have a 1 millisecond deadline to be able to regulate that force. So just given the tensile stress of the material and inaccuracies in your actuators, you do need to kind of reduce and increase pressure derived from your actuators, and that regulating force is very low latency if you want to do it well and not drop or crush the material. Walking robots have to contend with gravity and have to contend with the reality of potentially tripping over things. And that requires a much lower deadline than, for instance, driving robots that need to make decisions about how to drive their wheels, but don't need to worry about tripping and those types of things. So that's the difference between a 4 millisecond response time and 100 milliseconds response time. And you have manipulating robots that are trying to grasp something and then move it around, right? And that moving action, especially if it's like a handle on a door, needs to be very carefully orchestrated and requires generally a relatively small deadline. You should definitely take all these deadlines as kind of the order of magnitude. This is probably between like 10 and 80 milliseconds. but take it as kind of an order of magnitude, rules of thumb, right? And if we have anti-lock brake systems or traction control systems, these are systems that, again, have to work on deadlines between 10 and hundreds of milliseconds. So you can imagine there are all these deadlines for actually interacting with the real world, and our computational system has to somehow fit within that. So how do we do that? We really want to think of the goal of these systems as effectively having the response time or the responsiveness of tasks being less than or equal to those deadlines. So when a task wakes up because of what we will call an activation, usually from either a timer tick firing and saying, hey, you wanted to wake up at this time, you need to execute and interact with the physical system, or because some sort of a sensor caused an interrupt and caused us to wake up. Between when that happens and when we're able to complete our execution and send commands to the physical actuators, we should be able to do all of that within our deadline, right? So that is the goal of real-time systems, of real-time scheduling algorithms. But to do so, we have to make a number of assumptions about the computations that are executing on our system. And this is really what derives a lot of the difference between these systems and things like Linux, where we really can't assume much about the applications that are running on our system. So what do we assume? We mainly assume two simple parameters. One is that all of the threads or tasks on the system are recurring. So they're going to do some execution, go to sleep, do some execution, go to sleep, and the time, or the period as we call it, between those subsequent activations is what we call the period, right? So when we wake up and want to do some calculation, and then the latency between that and our deadline is effectively the period. And that also happens to be the time when the task will activate again to do its next computation. There are more complicated task models. I'm going over the simplest possible one. We also need to assume that we know a priori how much computation each of these tasks will do. So we call this the worst case execution time. And this is a really, really big assumption. This is essentially saying that when our tasks activate, we need to not just be able to guess how long they're going to execute, but actually know a priori the maximum amount of time that they're going to take to execute. And this is often derived through just experimental measurement. We'll run the system for a month and essentially measure the worst case execution time of all of the tasks on the system, and then sometimes multiply it by 2 if we need to be really safe, and use that value for kind of our value here that we're assuming. So most of these real-time tasks do fall into this type of an execution behavior. We'll have some sort of an infinite loop. They're basically going to be controlling the real-time system for till they're powered down. So they just are going to be in this loop for the entire time. They're going to wake up at the next period. So they essentially have a call to basically say, hey, block me until my next period activates me. So they block until the next activation. They read some sensor value and they do some computation. And the sum total of this reading the sensor value and doing the computation needs to be considered the worst case execution time. And then after they're done doing that computation, they send it out to the actuator, which is part of that computation. They go to the next iteration of the loop where they block until the next period, right? So they're recurring, they execute every period, they do some computation, right? So putting all of this into one place for every task I in the system, so we have a number of threads or tasks in the system, we're going to call them I here. They each have a period, PI. This is a span of time for their repetitive execution. Task activates and wakes up every PI time units. They have a worst case execution time, which is EI. E kind of stands for execution time here. The worst case execution time essentially means that every activation, tau I executes for a maximum of EI time units. So They might, for instance, activate every 10 time units and have a worst case execution time of 2 time units. So they execute 2 time units every p time units, right? And we're assuming now, for simplicity, that the deadline of that task is the next activation time of that task. So as it is at the end of the period that it activated in. And a system is just defined as having a number of tasks or threads in it, tau 0 through tau n. And if we draw this graphically, we have a situation like this where we're proceeding with an increasing time going from left to right. So as time flows in the system, we're going to be adding execution into the system. And if we have a single processor system, a single core system, we know that a single task will be able to execute at any given time. So if we look at tau 0 in the system, the up arrows indicate when it activates. So we can see that every P0 time units, it activates. So at time 0, at time 3, at time 6, at time 9, and at time 12. And we can see that there is a worst case execution time of E0 within that period. Now it might activate and run immediately if it's the highest priority task, but if it's not, it might actually execute a little bit offset from when it actually activated because other higher priority tasks executed immediately when it activated. So we can see that the task activates and executes, and all of these executions happen before the next activation, so this task is meeting all of its deadlines. We can see that we can have many tasks executing in the system. This would be tau 0 through tau 4, and they all have these types of executions at different points in the system, right? And if we assume that tau 0 has a higher priority than tau 4, what we can see is tau 4 executes at time T0 at time 0 basically, and it has its activation its period, therefore its deadline pretty far into the future. And we can see that its execution is broken up into multiple pieces of execution across the timeline. And that effectively is saying that it was preempted during each of those holes between when it started executing and when it finally finishes. It was preempted by the other tasks, right? So this shows essentially a timeline with different tasks executing at different points. Don't try to read into this too much for like priority assignments or anything. I'm just using this as a broad example of how we draw this all into a system, right? These preemptions that I was talking about are due to a prioritization, like I said, right? So somehow the scheduling policy needs to have prioritization as a key part of its logic. So the high priority tasks preempt and execute in lieu of the lower priority tasks, right? So we can think of priority in many different ways. One of the ways, and it's the most intuitive way, is called fixed priority scheduling. Each of the tasks in the system is essentially assigned a different priority, and here we just call it delta I. And if there are multiple tasks that are in the run queue at any point in time, the one with the highest priority is the one that should execute. As the second homework in the class, you implemented an O of 1 priority queue. That is quite literally the data structure that is used for most of these systems. So you want an O of 1 algorithm for deciding the highest priority task, and it uses that type of a thing. There are, however, dynamic priority scheduling systems, and this is just to say that the priority of the different systems will change over time. And earliest deadline first, which is actually very well named, it's EDF, earliest deadline first always chooses the task to execute that has the earliest deadline. So the task with the closest deadline to the current time is the one that executes now. It is a dynamic priority system because the deadline is effectively the difference between the current time and the deadline, right? So that changes as the system executes for all tasks. So with EDF, we always execute the task with the earliest deadline. EDF has a lot of huge benefits. It can get higher utilization out of the system, but unfortunately, we don't have time to go over any of that. I'll only discuss fixed priority. I want to talk mainly about how fixed priority works and how we integrate it into a system to make global guarantees such that we can say that all tasks will have their deadlines made, right? So, Fixed priority just says that we're assigning a priority to each task, but it leaves open that question of how we assign a priority to each task, right? So how do we assign these delta i's, the priorities, to each of the tasks? So let's choose a very simple system where we have two tasks in the system, tau 0 and tau 1. They have an execution time of 2 and 4 respectively, and a periodicity of 5 and 10 respectively. And if we choose that tau 0 has a low priority and tau 1 has a high priority, then let's think about what will happen. Before we kind of dive into that, I want to note that if we kind of do the calculations for over a window of 10 time units, how many of those time units are spent doing execution, only 8 out of 10 of the time units are actually spent doing execution. So because the system is only 80% utilized, you'd really imagine that this would be able to do stellarly, right? But let's think about it. I want you to actually think through this system. If we have tau 0 at low priority, tau 1 at high priority, do we actually meet all of the deadlines in the system? And we'll use the intuition that you derive from this to kind of form a more concrete policy for deriving mathematically whether we can meet the deadlines. So I want you to take this seriously, do think about this for a couple of minutes, come back, pause the video, I'll go over the answer after. Okay, so this actually does not meet all deadlines, and let's go through why. So tau 1 has a higher priority than tau 0, right? So that means that if we draw these on that timeline, both tasks are active at time 0 within the system, but because tau 1 has a higher priority, we choose it for execution at time 0. Because tau 1 executes for 4 time units in the worst case, and it completes, the down arrow means that it completes its execution, we know that it will meet its deadline because it does do its 4 time units of execution before its deadline of 10 time units into the future, right? But because tau 1 had a higher priority, tau 0 is only able to start executing its task at time 4. When tau 1 completes its execution. And it takes 2 time units to execute. Remember, it has an execution time of 2 and a period of 5. So it takes 2 time units to execute, which means that by the time its deadline arrives at the start of its next period at time 5, it has only executed 1 of its time units, not both of its time units. This means that it has not sent the result of its computation to the actuator, therefore the system hasn't received the physical commands of what to do by the time that they needed to be arrived. So therefore, we have not actually met the deadline, which is what the X means here, right? We complete our execution 1 time unit after the deadline, which means that we did not meet our deadline. Now this is interesting because again, the CPU is only 80% utilized, so we aren't using the CPU entirely, so it feels like we should have done better, right? Can you use the intuition that we've gleaned from this to actually figure out how to assign priorities to each task? So we can go back here, think this through, pause the video. How might we assign priorities here? Now, for this specific case, it's obvious we probably want to flip them, but can you come up with a kind of algorithm for assigning these priorities? Think about it for a second, pause the video, come back. So there are many ways to assign priorities. One of the oldest and a decently effective way to do it is using what's called a rate monotonic assignment. That is a very, very fancy way to essentially say that if you have a lower periodicity, you should have a higher priority. Which is equivalent to saying if you have a faster rate, you're kind of executing with many activations more than another task, then you should have a higher priority, right? Lower period, higher priority, higher period, less frequent execution, lower priority, right? So if you have infrequent execution, you effectively have a lower priority, right? So if we look back at this example, the tau 0 should have a higher priority because it has a lower period. It is going to execute with activations more frequently than T0, which has a higher period, therefore should have a lower priority, right? This is rate monotonic assignment, and if we do that, we can see that tau 0 now has a higher priority, so at time 0, when they both want to execute, tau 0 is chosen by the scheduler. It will meet its deadline by completing its execution at time 2, which is before its deadline at time 5. And then we will execute tau 1. It needs to execute for 4 time units, but you can see it's not able to because at time 5, the second instance of task T0 activates because it activates periodically at, in this case, time 5. It will execute for 2 time units because that's what it does. It will meet its second deadline, and then it will... because it's done, the only task in the run queue at time 7 is task tau 1, so even though it has a lower priority, it's the only task to run, so we execute it for its last time unit to finish its 4 time units of execution, at which point it's done. It completes its execution before its deadline at time 10, and we have both of the tasks meeting their deadlines. Yay! Victory! Cool. So rate monotonic priority assignment seems to do relatively decently, right? Now, we're doing a lot of kind of theoretical work here. We're defining a model to describe the system. The model is now kind of the period, the worst case execution time of each of the tasks, and a priority assignment to each of them. This is nice because now we have a model that we can use to analyze the system, right? So a model here, which we have now defined, is just an abstract description of the system. It doesn't talk about all the details about what the computations are or any of that. It just provides a model of the system. All models are wrong, some are useful, is the famous saying, right? So a model lets us talk about the specifically specified idea, right? The details that are captured in the model, it lets us talk about them rather than all of the messy implementations where it's hard for us to actually say anything concrete about it, right? So the goal of real-time systems is effectively to have an implementation, including some policies that allow us to kind of instantiate a model, so fixed priority scheduling with a priority assignment. It allows us to have a model, which is a mathematical description of the implementation, and hopefully that implementation adheres to the model. And then the last thing that we haven't talked about is that we want to define an analysis, a mathematical analysis whereby we can derive properties from the model. And this is where we can make global statements about the system, for instance, meeting all of its deadlines. So we want to take an implementation, derive a model that describes the important parts about it that we can then analyze and be able to say something globally about the properties and behavior of the system. So let's dive into that last part, which is an analysis of the system. So for an analysis of the system, what we want to do in real-time systems is show that the system is schedulable. Whether a system is schedulable or not is answering the simple question of can the system meet every task deadline. If we can show that for a given model that an implementation adheres to, every task can meet its deadline, every deadline within the system, then the system is schedulable. So what we're actually looking for is a mathematical analysis that can use the properties of the task model that, again, describes the implementation to make sure that the real-time system controls the world predictably, which is to say, each of the tasks will be able to meet their deadline. So this is really cool. We're trying to say something about the physical properties of the system by deriving a mathematical analysis that analyzes a model that uses the implementation, that uses this notion of an abstraction of a deadline to map out to the physical properties of the system. This is so many layers of abstraction, and the abstraction boundaries are crossing between conceptual ideas like deadlines into implementation, into mathematical models of the system. This is one of the reasons why real-time systems is fun. You need to implement something that adheres to a model, and then you get to say mathematical things about it. You can actually speak with certainty about your system. It's really cool. So let's go over an analysis. Let's say something mathematical about our system, right? Let's say whether it's schedulable or not. So first we're going to assume fixed priority scheduling. We're going to assume that there are priorities given to each of the tasks. And what we want to say for a specific task is what is its maximum response time? What is its maximum bound to complete its execution every activation? Basically, can we actually put a bound on the response time? Up till now, we've been talking about response time as something that we're kind of trying to optimize for within the system, but it's always a little hand-wavy whether we're getting there. Our goal now is to specifically say, is our response time within the deadline? And if we can say that for every task in the system, we can say that the overall system is schedulable. So the intuition behind what we're going to look at, a response time analysis in RTA, this is a brilliant analysis created by Neil Audsley and Alan Burns and people from the University of York. And it's just brilliant because of its simplicity. You might not understand every aspect of it through this lecture, but I think you will understand absolutely most aspects and a very high-level idea about how it's applied. So what we want to be able to say is that over some window of time, which we can choose, for instance, as the period or something smaller than the period, what we want to do is calculate what's called the interference, which we'll call the IF, a function called the IF over that window. From the higher priority task for a given task. And what we're essentially trying to say is if the interference from all of the higher priority tasks, when they kind of steal execution time when we could have been executing, but instead they're higher priority, so they got to execute. If we can mathematically describe what that interference is over, for instance, our period, which we see here for an interference over our period, and we add our own execution time to that, if that total is greater than the period, then we cannot make our deadline and the system is not schedulable. But if it's less than or equal to the period, maybe it is actually schedulable. So what we want to essentially do is get some mathematical equation to describe this interference of the higher priority tasks on us, okay? So let's do this starting with some examples. So how would we actually calculate the interference? The first scenario is that we want to calculate the interference for task T0, where T0 is low priority. So we're going back to a system that does not use rate monotonic priority assignment and instead has this kind of periodicity of 5 higher rate task with a lower priority. And we want to actually calculate the amount of interference for T0, right? So if we think about this, what we essentially want to do, the intuition is we want to say, well, okay, if T1 has a higher priority than T0, then we know it will execute over a window of time before T0 does, right? We need to assume that they both activate at the same time because we're looking for kind of a pessimistic value here. So we know that we should get 4 time units of execution for task 1 for the as interference on task T0. So if we take that interference that tau 1 is causing on T0, we can sum that with the actual execution time of T0, so 4 plus 2, and we can see that that value of 6, 4 plus 2 equals 6, is greater than the periodicity of T0. So we can see that that is not going to make our deadline. So this notion of interference is actually kind of what we calculated here intuitively. The interference from tau 1 is that 4 time units because it had a higher priority, right? Okay, so I don't think this is that complicated when we go over a very simple example. Let's go through another example. Now we have 3 tasks, tau, T0, T1, and T2. And we have T0 at the highest priority, T1 at the middle, and T2 at the lowest priority. And they have these execution times and periods. You can pause to digest those execution times and periods, right? And I'm actually going to annotate each of these tasks with a different color here. And we're just going to lay out those colors in that kind of execution diagram to get an intuition what's happening here, right? So we want to calculate the interference on T2 from tau 0 and tau 1, right? So we are calculating tau 2's interference of the higher priority task, therefore tau 0 and tau 1. Okay, so we know that tau 0 has the highest priority, so it will get 1 unit of execution every 3 units of execution, so it should have that 1 execution of interference on tau 2. But we also know that tau 1 should have some interference on tau 2. But tau 1 will be able to execute for only 2 time units before actually tau 0 wakes up again and is activated because its periodicity is 3 time units. We've executed those 3 time units, so it will preempt tau 1 and execute for its second activation at that point. So this is why we see the tau 0 executing, then tau 1 executing for 2 time units, but then being preempted before it finishes its 3 time units of execution, right? But then, after tau 0 is done executing, then we only have tau 1 and tau 2 in the run queue. Tau 1 has higher priority, so it will get to execute, and then the only task left in the run queue is tau 2, so then it will get to do its 1 unit of execution time, right? So what we want is an algorithm just to be able to do this kind of manual calculation that we just did to calculate that interference. So here we see that there's 2 time units of tau 0 that are interfering and 3 time units of tau 1 that are interfering for a total interference of 5 time units. And then we need that 1 execution time of tau 2. So we can see that we finish execution at time 6. For tau 2, that is less than its deadline of 9. So it would actually be able to meet its deadline in this case. We've calculated the maximum amount of interference. And if that maximum amount of interference is not enough to push it past its deadline, we know that it can meet its deadline. Okay, so the question is, how can we actually formulate an equation for this, right? We want to calculate this interference of all of the higher priority tasks over some window, right? So in RTA, a response time analysis, we're going to calculate for a specific task. That's why we have here RTA sub I right here. Hopefully you can see my mouse. So we have RTA sub I over some window. This is what we want to calculate. The equation for that is something a little complicated, and I'm going to go through the logic behind this, but this bold-faced part of the equation that I'm emphasizing here is roughly equivalent to that interference calculation. That is the term within this equation that is trying to determine what the interference is from all the higher priority tasks. And what this is essentially saying is that I want to sum up for all of those tasks that are higher priority than my current task, the amount of interference from all of those tasks. Let me walk through it a bit at a time. So, what is calculated within this term? This term here, you can see the ceiling terminology. If you don't remember what ceiling means, that's basically just saying that the division within, you should always take the ceiling of the division, round up instead of rounding down, which is kind of the default on computers, right? So we're just rounding up. That's all that we're doing. And what this is saying is, well, if the response time analysis, the RTA, gives me a response, gives me some window. What this gives me a response time over a window. What this is essentially saying that I want to calculate over some window how many activations of a higher priority thread will happen. Kind of ignore right now the whole RTA window and -1 thing. We'll get into that. But right now, think of all of that as a window. And what we're essentially saying is how many periods of a higher priority task fall within that window. That's all that this calculation is doing. How many executions of a higher priority task fall within this window. And if we look back at this example, we can see that tau 0 had 2 periods falling within the window that we ended up calculating the interference within. We needed to look at the execution for tau 2 over a 6 time unit window. And we found that, of course, how many executions of tau 0 fit within 6 time units? Well, its period is 3, so 2. So we needed to look at 2 of its executions. That's all that we're calculating here. How many of the activations for each of the higher priority tasks could happen within a certain window of time. And then for each of those activations of that higher priority task, just consider its execution as part of the interference. So we're essentially saying, how many times could you activate? How much overhead do you have per activation? This product of both of those is simply the amount of interference that that high priority task can have over us. And then we're simply doing that calculation for every one of the higher priority tasks within the system, right? And then, of course, because we're trying to calculate how long it takes us to execute, we also need to, we also need to consider our own execution time. So we're essentially saying how much interference can we have from all those high priority tasks, which we're doing by saying how long do each of those higher priority tasks, multiply that by how many times they could execute within this window of time that we're considering, sum that up for all of the higher priority tasks, add our execution time onto it, and that's our response time. That is our actual response time. So that is essentially all that a response time analysis is doing. The complexity here with it kind of being a recursive algorithm happens to do with the fact that it is calculating the actual response time for a task, which is to say it's not trying to consider how much interference there will be within a certain window of time, a period. It is trying to actually consider the maximum response time that a certain task will take to execute. So what we do is we actually need to choose an initial window that will calculate this interference over. And for that initial window, we usually just consider the execution time of the task. So over the execution time of this task, how much interference can I get from the other tasks? Once I calculate that window of interference, including our own execution time, then I need to call the response time analysis to see how much interference there is within that window of time. I might get more interference from high priority tasks because of that. So what the algorithm for this ends up looking like is something like the pseudocode on the left. We track a previous window that we calculated the response time, the response time including the interference over, and we typically set that to be our execution time, this thread that we're calculating all this for, its execution time. And we simply calculate the response time analysis over that window for this task. And that is our initial value for our response time. And while the algorithm has not converged, which is to say, while the previous window does not equal the current window, we continue doing this calculation. And what that's essentially saying is, once I know that the response time analysis is the same over 2 subsequent iterations, it means that the window of interference is no longer growing. We're not calculating more and more interference from tasks as we calculate the previous iteration of interference. And once we've converged, that means that we know that is our actual response time. However, when we haven't converged, you see in the algorithm that we have this while loop. And we're essentially saying, all right, my previous response time, I'm going to save that as P. I'm going to calculate the next response time. And then again, I just compare that previous value with the next and keep on going. This is a slightly inaccurate algorithm because there's another loop condition. If we actually kind of calculate the response time analysis as going beyond the deadline, then we can stop because we know that we don't have a schedulable system. But for simplicity, I don't have that here. Okay, what does this look like? There's a very complex visual nomenclature that I have here. I apologize, so I want to go over that first. So notice that I have tau 0, tau 1, and tau 2 as different colors, the kind of light teal, the blue, and the purple. And all that I'm doing here is kind of annotating the actual values that are calculated from the response time analysis in one iteration with those colors. I didn't color the subsequent iterations just because you should see the pattern and be able to do the same. So the first thing is that the first iteration through the response time analysis, we set the window that we're trying to calculate the interference over to be our execution time, right? We're calculating the interference for task T2, therefore our execution time is 1. So you can see we're calling RTA with a value of 1. And we are essentially trying to calculate that we are trying to calculate like interference over that period. Therefore, that complicated RTA term essentially gets that 1 passed on through. So we're trying to say, all right, I know my execution time for T2, T2 is purple, is 1. So we see the value 1 as its execution time. I know that I have that overhead within the system. Then I have the ceiling of the window that I'm looking over, which is 1 over 6, which is the blue task, T1's periodicity. So how many times can T1 interfere with our task? Well, 1 over 6 till the ceiling is 1. So 1 times 3, which is its execution time, is 3. I can have 3 time units of interference from T1 on myself here. And then task T0 has interference, which you can see is the teal here. We're looking over a window of size 1. And over a window of size 1, we know our period is 3. 1 over 3 is, with the ceiling, 1, and our execution time is 1. Therefore, we have 1/3 ceiling time 1 is 1, right? So if we look at the amount of interference and execution time that tau 2 will have, considering only its initial execution time, we have 5 as its response time. So we know that it will essentially have this amount of interference, 4 plus 1. But the problem is we were only considering a period, a window of interference of 1. Now we know that we're going to be executing for a longer amount of time before we're able to calculate our response time, before we're able to actually finish our execution and wait for the next period. So what we need to do is calculate the response time analysis again, given that window of time. So now we're calculating the RTA given that previous window of 5. And a lot of things change here. Of course, because we're considering a window of 5, we plug that into both of these equations. And the big thing that changes here is that 5 divided by 3 ceilinged ends up being 2. We have 2 executions of tau 0 that will interfere with us. So therefore, this term goes to 2, and we end up getting an interference of 6. Now again, we've seen this before, right? We know from our intuition here that we had these 2 executions of tau 0 that ended up interfering with us. And all that we're doing here is calculating that and seeing that within the equation. That we can see here, we have 5/3 ceiling is 2 executions of tau 0 that can interfere with us. So then we need to run the response time analysis again with a window of 6, but this time we see that the outcome of this new RTA is the same as the previous, so therefore we know our response time is 6. And this matches the intuition that we had here when we calculated the response time of the task. So this effectively says, because the RTA that we calculated was 6, that we tried to calculate over a window of 6 equaled 6, those are the same value, therefore we are meeting the deadline. However, if we were to change, and you can see this here, the execution time of E2 to 2, now we're doing something completely different. We're starting the RTA with a window of 2, and we have 2 units of execution here for tau 2. Now we're because we're calculating over 2, we have the numerator as 2 here. Nothing really changes here. We essentially have 2/6, 2/3, etc., etc. We calculate 6. Last time we calculated 5, but that was just because we had a smaller execution time, so nothing really changes here. But now when we calculate the RTA of 6, we notice that again, maybe not much changes. We get 1 execution of tau 1 interfering with us, 2 executions of tau 0 interfering with us, which was the same as last time, but we have our 2 time units. So therefore, instead of a 6, which allowed us to converge last time, we actually have a 7 here. But when we try to compute the response time analysis over a window of 7, we notice that things change drastically. Now we get 2 interferences from tau 1 because it will be able to fit 2 times within a window of 6. It will want to execute 2 times then, and we get 3 executions of tau 0. So now these 2 values are much higher, and we have an amount of execution plus interference of 11. And 11, because its calculation for the RTA is higher than our period, is higher than our deadline, we know that we have not made the deadline, right? So this value of 2 actually blows up the system and prevents us from making our deadline. The system is no longer schedulable, right? Okay, so I want to back up and reassess where we're at. We have created a task model, right? That is an abstraction of the execution of the tasks within the system. It describes simple things like the worst case execution time, the period, and the deadline and the priority. We hopefully back this up with an implementation that adheres to the model, right? So we have to implement our fixed priority scheduler in a way. We have to that adheres to fixed priority scheduling. We need to make sure that our tasks in the system don't execute any longer than our worst case execution time. So long as they adhere to the parameters of the model, then we have a sound model with respect to the implementation. And if that's the case, then we can analyze the task model mathematically and show that if the response time analysis passes for all of the tasks, then the system itself is schedulable. This is awesome. We're now able to essentially say mathematically that the system adheres to physical constraints of a system, given a number of assumptions that we've made throughout the system. And there's a lot of research in assuring that those assumptions are sound. For instance, there are static techniques that are used to analyze code to try to ensure that it adheres to a worst case execution time. So there are research-based techniques to try to make sure that all these assumptions we've made along the way. But one of the coolest things about the response time analysis is that it actually deals with additional complications within the system. So what are some of these additional complications? First, we have a set of shared resources in practical systems. We've been talking about shared resources for the past, 6 lectures, right? These are essentially locks or something like them. If we have mutual exclusion, then we have some sort of a critical section that requires mutual exclusion. We call this a shared resource, right? So we have critical sections provided by locks around shared data structures that need to be shared between tasks. The weird thing about these mutually exclusive critical sections is that if a high priority thread and a low priority thread can both try to take that lock, then a low priority task could take the lock. And if it's preempted right after it actually takes the lock, and we switch to a high priority task that then tries to go and take that lock, the lock is contended. The low priority task has the lock. So somehow we need to consider a small amount of low priority execution through the critical section as an interference on high priority tasks. So low priority tasks can interfere for a critical section length of execution on high priority tasks. High priority tasks suffer low priority interference. This is crazy, right? How could we actually fit that into an analysis? Additionally, we've talked about this many times. Context switches aren't free. How do we analyze this? How do we fit that into the task model, right? So some of the assumptions we were making about the system is that this task model described everything in the system, but now we're seeing it doesn't, right? But can we somehow accommodate these types of physical effects in the system? And you can. One of the beautiful things about a response time analysis is that you can fit the execution time of a lock, the green thing here, into the system and fit it into a response time analysis to actually say whether the system is schedulable, even considering that low priority task execution through the critical section on the high priority tasks. And you can fit the dispatch latency of the system into the execution and the interference from high priority tasks. The intuition here is that when a high priority task executes, you need to switch to it. So you should count that switch cost. And then when the high priority task is done executing, you need to switch away from it. So you have 2 times the dispatch cost, the context switch cost. So you can see that fitting into the interference. So one of the really cool things about an RTA, response time analysis, is that it's so extensible. Okay, I want to take a step back a little bit, just mention very quickly, if you want to do these kind of response time analysis for multi-core, it works for partition systems, but you need different analyses for global systems. The preemption notion there is very different. I'm not going to go into that at all. I also want to point out that RTOSs are really complex. It's not just tasks executing independently. Here you can see that we have a number of sensors on the left that are feeding their data, that have tasks that read that sensor data, and those tasks might pass messages to other tasks, T3, T4, T5, which might do some computation, make some decisions, and pass their decisions on to the actual tasks that are communicating over Wi-Fi and sending commands out to actuators, right? These are T0A and T1A. And then those execute and actually send stuff out to actuators. They could be using channels or locks to pass all of these messages, but somehow they pass these. So there are dependencies between tasks. The RTA that we've talked about so far and the task model that we've talked about so far doesn't really accommodate any of this. There's a lot of research that's been done that accommodates these types of constraints. And this is something we really need to be concerned about, because the Mars Curiosity rover had 240 tasks, many of them which had dependencies. These systems get a little bit more complicated than I've been talking about now. So let's take a step back now and look at the forest from the trees, or the words from the bits. We have made a lot of assumptions about our threads' execution patterns and built models out of them and then analyses. This can be really powerful because now we can say whether an entire system is schedulable, whether every task will be able to meet its deadline. This is amazingly powerful, but is not general purpose, right? We can't assume that like Firefox or a movie viewer is going to adhere to these types of constraints, right? So that's why we have have things like Linux that are using things like CFS to balance the competing goals of the system of response time and high utilization, low overheads. And you typically use heuristics to do this. The 20 milliseconds, the 4 milliseconds, these are all heuristic values that may or not be correct. They're just what they chose, right? You might want to tune those to be different, but you're making no guarantees about the overall system's execution. So we've seen two systems today that make different assumptions about what how they can describe the tasks in the system, and they both try to do their best to optimize for the goals of the system, either meeting deadlines or trying to maintain good responsiveness while maintaining high utilization, low overheads, right? So hopefully this is interesting, and playing these two different systems against each other to show that the assumptions that we make about the system demonstrates that you really can never say whether one system is better than the other. It's all about what are the goals of the system and what assumptions are you making about the system. That is what determines the decisions that you make when you're implementing a system. So thank you very much. I'm sorry this was a long one. Have a great one. Bye-bye.